In this video, we'll talk about the other super important property of the determinant, and that's that it's multiplicative. So the result here is the following. If I have A and B two square n by n matrices, then the determinant of A times B is the determinant of A times the determinant of B. So if I multiply two matrices together, then take the determinant, that's the same as if I took the determinants separately and multiplied them over here. So this idea sort of makes sense if you think about the determinant in how it sort of scales areas and the fact that matrix multiplication is composition of maps. The determinant of a matrix really tells us how multiplying by this matrix scales volumes or areas. So if I have two maps, F and G, say F is going to double the area and G is going to triple it, then it makes sense that if I compose G and F, that this map should multiply the area by a factor of 6 because it will double and then triple. It's going to be 6 times overall. Now for linear maps and matrices, this matrix multiplication is composition of linear maps. So it then makes sense that if I have a scaling component, this determinant, when I multiply the matrices, I'm composing the maps, then the scaling bit should also multiply as a result. So the scaling on A times B should be the product of the scaling of A and B. And that seems super theoretical, but there's one particular way and this becomes very, very useful for us in doing computations. And it's the following. It is that the determinant of the inverse matrix should be 1 over the determinant of the matrix itself. So this comes from the fact that if I multiply A times A inverse, I get the identity matrix. That's how A inverse is defined. It is defined to be the inverse matrix that cancels it out in this way. But the determinant of the identity matrix is 1 because it's diagonal and has 1s on the diagonal, right? I, for some n, its identity matrix is going to be 1s on the diagonal and 0s everywhere else. And so its determinant is 1. Therefore, the statement of multiplicativity tells us that determinant of I equals determinant of A times A inverse equals determinant of A times determinant of A inverse. Since this is 1, I can divide both sides by determinant of A to get that determinant of A inverse equals 1 over determinant of A. Which is great, but what does that tell us? Well, this tells us that if determinant of A is 0, the matrix A cannot be invertible, because for any matrix, it has a determinant. It is a number, it's a finite number, and it's well-defined. So if determinant of A is 0, the determinant of A inverse can't be 1 over 0, because that's not defined, and so A inverse must not exist. The result from this, that we'll use a lot, is if determinant of A equals 0, then A is not invertible. This is also an if and only if, meaning that if A is not invertible, its determinant must be 0. And one way you can see that is using 2 by 2 matrices, because if we take the matrix A, B, C, D and take its inverse, it has a formula given by 1 over AD minus BC times DA minus BC, like that. And this thing right here is the determinant. So we have a 1 over determinant in the formula, which tells us that if determinant of A was 0, this would not be invertible because I can't use this formula. And if it's not 0, this formula works and gives me the inverse. So this will be our big way we're using this property here, by relating invertibility to determinants being 0, or not 0 respectively. So we have this example, is the following matrix invertible? Explain how you know. So the main way we're going to do this is using determinants, because we know that if determinant of A equals 0, then not invertible. And if it's non-zero, then A has an inverse. And I'm not asking you to find the inverse, just asking you to determine if it is invertible. So we're going to find the determinant. We can do this several ways. So what I'm going to do is look for the most zeros I can find to do this with cofactor expansion. And so I see this second column here has 2 zeros in it. So I'm going to use that to find my determinant. So determinant of A should be -1 to the power 1 plus 2 for row 1, column 2, times the -2, times the determinant of the minor, which is I want to take out that row and that column, and write whatever's left. And then plus -1 to the row 3, column 2, times a 1, times the determinant of that minor, where I now remove that row and that column, and write what's left. So now let's work out those two subdeterminants, and then we'll come back to our expression here to finish up the problem. So we have here 1, 2, 1, 0, 3, 1, 2, 1, 2. I'm going to expand along the first column since it has a 0 in it. So I get -1 to the 1 plus 1 times 1 times the determinant of 3, 1, 1, 2, plus -1 to the 3 plus 1 times 2 times determinant of 2, 1, 3, 1. This is a 1 times 6 minus 1 plus 2 times 2 minus 3. So that's a 5 minus 2, 3. And then our second subdeterminant here, I'm going to expand along row 1 for this one because there's a 0 at the end there. I get -1 to the 1 plus 1 times the determinant of 2, 1, 1, 2. And then plus -1 to the 1 plus 2 times 3 times the determinant of 1, 1, 2, 2. So I get 1 times 4 minus 1. And then plus a -1 times a 3 times a 2 minus 2. So that's all 0. Meaning this is another 3. Then going back up, I know this here is 3. And this here is 3. That'll be a -1 times -2 is a 2 times a 3 is a 6. And then minus 1 times a 3 means determinant here is 3. And then we can get our result. So since determinant of A is non-zero, that means this matrix is invertible. Now, a second way we could have solved this out is using row reduction. And we'll show that method next. So with the row reduction method, we just want to reduce this matrix. So we see we already have 1 in the top corner here, so I can leave that alone. And I want to use that 1 to get rid of the 1 and the 2 below it. So my steps here are going to be R2 is R2 minus R1, and R4 is R4 minus 2R1 to get rid of those numbers. The top row stays the same. 1 minus 1 is 0, 0 minus -2 is plus 2, 2 minus 3 is minus 1, 1 minus 0 is 1. Third row stays the same. 2 minus 2 is 0, 0 plus 4, 1 minus 6, and 2 minus 0. Now there's two options here. I could either divide row 2 by 2 to put a 1 in this spot here, or I could swap rows 3 and 2 to get that 1 up there. Let's go with the swap method. And now I'm going to use that 1 in row 2 to cancel out the 2 and 4 below it. The first two rows will stay the same. For the third row, 2 minus 2 is 0. -1 minus 6 is minus 7. 1 minus 2 is minus 1. 4 minus 4 is 0. -5 minus 12 is -17. And then 2 minus 4 is -2. Now nothing here looks super convenient, so I'm going to just go for it and divide the third row by -7 to put a 1 in that slot, which gives the following matrix. And then I'm going to add 17 copies of row 3 to row 4 to get rid of that -17. So I will get a 1, a -2, 3, 0, 0, 1, 3, 1, 0, 0, 1, 1 7th, 0, 0, 0, and then -2 plus 17 over 7. Which this here is 3 over 7, because -2 is -14 over 7. So if I call this matrix here M, my work before on row reduction and diagonal matrices and triangular matrices is that the determinant of M is 3/7. But how does that relate to determinant of A? And that's the meaning of the different colors that I wrote the steps in before. So the green steps here do not change the determinant, right? Adding multiples of 1 or 2 do not change the determinant. Doesn't change, doesn't change, doesn't change. But the orange steps here do. So I started with A. I did one swap, that adds a minus sign. And then I multiplied a row by negative 1/7, so the determinant was also multiplied by negative 1/7. So in going from A to M, I did one row swap and multiplied one row by negative 1/7. So this means that the determinant of A times a negative 1 from the row swap times a negative 1/7 for the multiplication equals determinant of M, which was 3/7. If we solve this out, we get that determinant of A is 3, just like before. So depending on how you're feeling about the matrix, how complicated it looks, you may want to use row reduction as well, and the method will also work to get you the determinant of that matrix. If you get used to the process of row reduction, it can be an easy way not to worry too much about cofactors to get to what the determinant of a matrix is, and then answer questions like, is this matrix invertible? Well, this determinant is non-zero, so therefore this matrix is in fact invertible, and we can get that both by cofactors and by row reduction.